So this connected film is done by Tiffany Schlane, who is a Berkeley graduate, co-produced by her husband Ken Goldberg, professor in ECS. Pretty exciting. So whenever something like that happens and has a premiere, we're all pretty excited on our side. And if you notice, on their main web page, it's open in limited release. Oh, I don't know. Opening this weekend, Berkeley Shattuck 10. So I'd like you all to see that. Just as a fun thing. Not a requirement, but a fun thing if you can do that. Connected, go see it. All right. 3, 2. All right, folks, welcome to 61C Lecture 8. Woo! Still keeping the whoa. And there was much rejoicing. Woo. All right, gotta keep the love, folks. Gotta keep the love. Today is getting a little deeper than we've done before with MIPS instruction representation. Actually, we are going to represent our MIPS instructions we've learned so far in ones and zeros. That's part of what we're going to do today. For technology in the news, the really interesting and revealing article from the New York Times about so many gadgets, so many aches, which say that many of the aches and pains many of us have nowadays at this young age are brought on by ourselves. The fact that we have laptops which do not meet ergonomic requirements of having the screen be this high but the keyboard being down here. Your keyboard should be at a right angle to your, and the screen, the top of the screen should be at your eye level, and no laptop has that unless a laptop has a screen that's this high. So, and you're only looking at the top 5% of it. So that's not so good. That's number one. Number two is your thumb only has 2 joints, your fingers only has 3, so the worst thing you can do is be typing with your thumb, which is how everyone does typing on the iPad. Also, you shouldn't use touchscreens heavily for typing because they have no give. The whole reason the keyboards are comfortable is they have a give and they kind of absorb it. If you're literally hitting, it's like, who would say, want your head to just go bonk, bonk, bonk against the wall? But that's exactly what you're doing is by ramming your thumb against this glass screen that has no give, right? So that's really bad and should not be used heavily for typing. You know, dragging is fine, clicking, touching this gently is nice, but when you start typing, bad stuff. That's what the New York Times article says, by ergonomists. Ergonomists? I don't know. And texting, this is a great quiz. If you want to get injured, do a lot of texting. So you might want to limit your texting on that. And I think there's a killer app, which is voice to text. You know, I see a text and I just say, boop, and I just say my response. And if it can have like 99% accuracy, I would use it. We can then imagine people using that while they're driving. That solves the driving while texting problem. If there's this huge unsolved problem ready to be solved. Yes, question? Android has swipe for typing, which I love. I think that's a great. You know, the world record guy is a swipe guy, and that's much better. I mean, think about swipe, right? You touch it once and just moving it around, way better. You might still have issues with the musculature, but at least the issue of hitting it, not so good. Okay? All right, let's keep on. So I want to, again, give a shout-out to anybody watching internationally. Zhao Tan from China. How you doing, my friend? Anybody else who's watching internationally or around the world or even nationally, email me, ddgarcia@csberkeley.edu. We'll give you a shout-out to know that we have some global lurkers. In review, what you've seen so far is shifts, set less thans, which allow you to do conditionals on inequalities. We can now load other things other than words. We can now load bytes. We learned about what unsigned means, and we added a couple more instructions to our repertoire. Today, we're going to be looking again. We're kind of looking a little deeper today, and then we'll come back after 2 lectures on looking deep, and we'll look broadly on how you make function calls. We haven't yet seen how to do that so far. This is the rough abstraction list you may have seen in the early slides. We started C, you compile down to MIPS, you assemble down to machine language. This is the ISA instruction set architecture, huge abstraction line. We draw it with a big pink thick line. And then you interpret that in terms of building a machine that does that. How is this machine built? It's built with small or low-level logic circuit systems. So you have this, which is a swap. That becomes this, which you now know is a swap. Look, it's so cool. Okay, so you now can grok that. It's pretty cool, right? You guys get that? Isn't that neat? I think that's pretty cool that you guys know how to do that. This is what this red assembly turns into a machine language. That's actually the MIPS code for that. Today we're going to be looking at exactly that issue. These are the pieces here. And again, today is this piece, today and Friday. And we'll have a guest awesome TA covering Friday's lecture, so please give them all the respect you give us. So today, This is the first time I'm really revealing the hood on how MIPS really works. We talked about it a little bit before. I remember Christian had a question. Other folks have had a question about the zeros and ones that get mapped to that. But today we're going to be thinking about that. Before we even start, we're going to be looking at the early big idea, a really big idea that you have taken for granted all your life because it has existed for as long as you've lived. It's called the stored program concept. So that's really huge, and we'll talk about that. Then instructions as numbers, meaning how do you make those structures become zeros and ones? How do you encode them? And then we'll look at actually doing that for adds and for data transfers. Okay? So here's a really big idea. The big idea is that in the olden days, you built a machine over here, and then you programmed it by turning switches. That's how you programmed it. Okay? And so they were the machine that actually did the calculation, if you look at the early days of the ENIAC and the like, here's this big machine with vacuum tubes, and here was the programmers. You know the programmers were all? All women. They were the first programmers. It was awesome. They were all doing the program. They were the smartest people in the group that could do that. So that was awesome. What was the big invention? The big invention was these switches were putting a program in. Why couldn't that program, but you're operating on data, right? The program is, you first wire it. By the way, you hardwire it for a problem. So you actually rewire it for the problem. And then the switches are you put the data in. And there are lights to put the data out. So they said, the data in is switches. Why couldn't the program itself be switches? Do you kind of get my idea? So rather than rewiring it to reprogram it, you actually have the program be stored. The program is what you're running, and now you have a general machine that doesn't have to be rewired for every time. Remember the olden days, the phone person say, I want to call somebody. You see the operator would say, okay, you want to call? And they would pull two wires out and plug it to here to here. They would manually do that. That's essentially what they were doing to program these early machines. The idea that the program can be part of the data is so cool. Here's switches for the data. Here's switches for the program. Pretty cool stuff. That's a really big idea. So the stored program concept you've grown up with because essentially you've inherited. The moment you had a floppy was the idea that the program is stored as data here, right? The program and data lived on the floppy. That didn't used to happen that way. You have general machines like that. That's huge, okay? And that also simplifies our world. Because if I'm at my job as the person running MIPS, let's say I'm building a machine to run MIPS successfully. And I'm thinking, okay, well, I got to run MIPS. Then I have to have some mechanism for loading the program in, which is a different mechanism from loading the data in. Like the guy that talks to memory to do the data manipulation must be different than my program manipulation. But no, because stored program concept, it's now the same guy. The program is in memory as your data is, and now it all makes sense. So it's the same. All of our hardware becomes easy, and memory can be used for data and instructions seamlessly. So the consequence is everything is addressed. Every single instruction you're going to say, I told you that a C instruction might map down through the compiler to several MIPS instructions. The idea is each one of those lives in a place in memory. Because I'm going to take my program, which starts on disk, and when I say run the program, it's going to load it into memory. And it lives in memory. Each instruction is going to be a word wide, and that means each guy gets gets some address, which are differences by 4 bytes every time, right? 1000, 1004, 1008, etc. C pointers is really cool. The pointers point to all of memory. But guess what? We're going to see that all of memory, some part is my data up here and some part is my program. So they both share the same space. And you can ask, if that's true, then guess what? Ain't no free lunch, right? It's a zero-sum game. If I have a really big program, let's say I'm simulating an operating system. So I loaded a big program, guess what? The amount of data I can get to is much smaller because my program it's eating into the same space I'm using for my data. Or if I have a really small program, I can have big data, which is kind of cool. Conversely, if I have big data, I can't write a big program in there. So your pointer, you could actually have a pointer, a C pointer, which goes like that electric wire, could actually point to a place of your program, data of your program. We're going to actually see rewritable programs. I'm going to show you a piece of MIPS code that has the pointer set to where the code is and starts to poke at the memory and rewrite itself. It's so cool. So, and all that's because pointers can go anywhere, and at the MIPS level, you don't even care. They're just a pointer. I'm just loading and storing words. I happen to be loading and storing from the instruction space versus the data space. Who cares? Well, the system that might prevent you from doing that, but at the point of view of, let's say the system let you do that, then that would be the case. The key piece you hear here on this slide is you need to have somebody keeping track of what piece of, here's my memory wall. I always talk about this huge memory wall. Where in memory am I currently living? You ever trace C by hand? Who's ever traced C by hand? Give me some love. Who's ever traced scheme by hand? Trace any code by hand? Come on, give me some love for the hand traces. Who uses a finger when they trace it by hand? The finger is where you are, right? I'm here. Oh, jump to foo, and now I have to jump down here, but I have to kind of remember where I was before to go back so that when foo finishes, I go back to where I was in Maine or something, right? So the finger is what essentially we're storing with our PC. PC stands for program counter as well as personal computer, kind of an overloading term there. And PC is where I am at any one time. Okay? So PC is going to be a value. How big is PC? How wide? How many bits? Your instruction space. It's whatever your word size is, 32 bits, because I have to be able to address anything. I'm basically asking how wide a pointer is. So the answer is, in our system, obviously 32 bits. Okay? So, and by the way, I guess Intel calls it an instruction address pointer, which is better than program counter. Because what are you counting? You're not really counting anything. It's really an instruction address pointer. It's where you are in your instruction address space. Okay, so because of the stored program concept, as a consequence, programs are distributed into binary form. We love that idea. You can now download programs, all those things you grew up with, but this was, again, a big deal when it first came up. It also means that you have different binaries for different architectures. That leads to an issue of backwards compatibility when you're thinking about an instruction set architecture you're defining. I'm explaining to you the MIPS instruction set architecture. Other architectures have had to think about backwards compatibility as they've moved forward, and the Intel 80x86, which becomes the standard, is used in almost every PC now available today, now that the Apple world has gone over to Intel as their core. 8086 was 1981's instruction set architecture, and as I mentioned before, you can take a 1981 executable, the game Snapes, I think I played with the deep, deep, and you kind of shoot things in this maze. It was really fun. I played it for hours. I could run that today. It might not be smart enough to be able to, many times games run assuming that the clock is exactly what the clock is of that day, and so you run these old school games and then it goes, and like, wait, I didn't even start it, and it's over because it doesn't slow down for what real time is. Sometimes they're done that way. It may be smart or dumb, who knows? Anyway, that's kind of cool. So instructions are numbers, right? Stored program concept means instructions are numbers. Instructions are going to be stored somehow. Well, they're numbers because we encode everything. We know that we can encode colors with bits. We can obviously encode instructions with bits. So here's the idea. Each register is a word wide. We know that. Okay, load word and store word both access memory one at a time. So each instruction is going to be a word wide. This add T000, it has to map to exactly a word because we're going to store instructions just like we stored words in our memory, and we're going to load and store words, which really could be grab an instruction, put it back there, or grab a word of data, put it back there. Same thing. Same load word and store word for getting instructions and for getting data. So here's the idea. We have 32 bits wide as our word. We're going to divide them into fields, which is kind of like a delineation, a dotted line around these bits have some semantic encoding, and these bits have some semantic encoding as well. That's the idea. We also want to have the fewest different formats as possible. Every additional format means more work for you when you're running a MIPS emulator or when you're writing hardware to run MIPS. So you want to have the fewest types as possible. By the way, parenthetically, there's a lot of seats, folks. People are sitting in the aisles. I don't know if you want to sit in the aisles. Look at, raise a hand. How many of these? I count 20 seats in the front, and there are 20 people. Do you want to come join us? And come on. Let's everybody get up. Come on, everybody get up and join the seats. Look how much more comfortable you are. Your back is hurting. Ergonomics, right? Ergonomics first was my first slide. Come on back. Let's give a hand to people. Go get a seat. Yeah. Let's come on up and make room for them. Let's all be a family here. And as a meta point, those of you coming in early, please go to the middle and leave the blank seats at the end, right? So that would be easier. Come on in and find spaces, please. A lot of space. You can back if you want to sit in the front. You don't have to sit in the front if you don't want to. I'm not that scary. Okay. So we talked about, unfortunately, wanting to have the fewest formats. Come on in, there's a lot of room here. So you want to have the fewest different kinds of formats so that your hardware is easier, right? Okay, that's nice. However, we've seen at least a couple of different flavors of instructions. But I'm going to give you a gift. We as the MIPS engineering design team, were able to cluster them into only 3 different exceptions. Remember I said there's all these exceptions, I have to kind of apologize for that? After it's all said and done, there's only 3 different kinds, which is actually not that bad if you think about building hardware, okay? 3 different kinds. I, J, and R. I stands for immediate. J stands for jumps. R stands for register. And those are the key 3. I, whenever you have an immediate, that's useful. It's also, you're going to see we use it for load and store word because that offset, guess what, can be a big and small number, just like it. We treat it as immediate, and guess what? We can use I format for my loads and stores, which is very nice. Okay? Shifts are a little bit complicated. I'll tell you what shifts are about. Because, see, the I means that constant you give me should be treated as a signed number, right? It's the amount I'm going to maybe branch up and down. It's the amount I want to be able to have an offset that I add to it. I'm always thinking of it as a number, which can be plus or minus, that I add to something else or use, right? It's this range. But shift is an unsigned number, right? It's from 0 to 31 is how many bits I want the front row to get up and slide over and sit down again, right? So you don't want to think about it as a negative number, so that's why you don't kind of consider the shifts as an I. Even though there is a constant there, it's a different thing. It's a 0 to 31 constant, different than this huge minus 2 to the 15th to 2 to the 15th number. Okay, so R is the easiest. We'll do R first. So R has these fields. 6, 5, 5, 5, 5, 6. The anally retentive symmetric person in me who has to have his speakers exactly the same left and right is very pleased with this format because it's nice and symmetric right there. 6 is on the ends and 5's in the middle. And the reason we do this, we're going to see, is the first thing you need to say is what instruction you're talking about. It's an add. You have to number that. An add or an add you or a sub. So you have all these things. All of those things get numbers. That's going to be the opcode. Opcode stands for operation code or an operator code. It is, you know that from 61A, the leftmost guy in a paren in an expression is the operator, and the other guy is the operands. So thinking of this as an operator code is not so crazy, right? We're going to see what we're going to call functions in a second. I'd say, well, it's a function. You're doing a function. Well, you're making changes to things. You're not a pure mathematical function, so not necessarily that, because sometimes you're doing a load word and store word and doing some side effecty things. RS, RTRD, STD, which is connected with your age group, I understand, for racers or something, but also for other things. So STD is easier to remember that. Then you have shamped, and there's always a channel of the Shaft, which is a funny 70s movie. There's always a shaft joke in there somewhere. But shamped is a shift amount, which is nice. Boom, boom, wacko, that kind of thing, if you've seen Shaft. And then function is interesting. So here's what we've got. By the way, everything I'm teaching you now is the time where you go to your green sheet. Everyone has the book. The first thing in the book is your green sheet. That green sheet has all this information in gory detail. And so you're not memorizing it. Hopefully you're not using any room on your study sheet for your midterm on this kind of stuff, because this is all your green sheet, and you get to bring your green sheet for free. So that's a nice thing. So on exams, always bring a free green sheet. We'll always have some, remember TAs, make some extra copies. People will forget them. It happens every year. 300 people, we have the higher percentage of that happening than other years. But you'll have a green sheet and your own study sheet. So don't waste your time on your study sheet on this stuff, because it'll be in the green. Yes, question? If you need a green sheet, it'll be one of the things that our TAs can get you. Yes. That's also, maybe you can place there's an online link to the green sheet. So make sure that's on, the webpage will have that pretty soon after it's already up there. So go to the website, just print it out, there's your green sheet. And print it in green paper to make it nice. All right. So, what have I got? On the slides and in the book, each field is viewed as an unsigned integer, not as part of a bigger number. All right, so let's think about that. So that means RS, 5 bits, is 0 to 31. Same with RT and RD. Same with shamped. Now it makes sense why shamped is here, not somewhere else. What's opcode and what's function? We'll talk about that in a second. Here's the idea. In R-type instructions, we do this weird thing, which you're going to see the reasoning for in a moment. This 6 is always 6 zeros. Okay. We did this in office hours today, so maybe I'll repeat myself for those of you, but apologies to those who are often in office hours. Our opcode is 6 bits. How many different instructions could I ever have then? 2 to the 6, you should have this memorized, which is 64. I want you to have that cold by the time the midterm comes up. So 64, all right. So I've got 64. You're telling me, Dan, you're only allowed to have 64 different instructions. What if I want more than that? Well, it turns out with R-type guys, once I specify STD and shamped, I've got these 6 extra bits. So the idea was, what if I made R-type all zeros? And when it is all zeros, I look to the function as the actual index for what it is. So it's like Opcode is 0. No, don't look over here. The function guy really has the answer. And then you look over here, and what this says is, I can have how many R-type guys? Go ahead, get loud. 64, because it's always a 0 here, but these bits can be anything. So that means I've got 64 R-types alone, and that's pretty cool. So that's one way we're going to cluster things. The 3 types have allowed me to say, I have a lot of R-types, and my R-types would almost fill up the whole opcode. So why not give R-types their own guy? And guess what? Fortunately, R-types have 6 bits to spare. So I set an R-type opcode as 0, and the function is I'm just explaining engineering. I'm not telling you how the world works. I'm telling you how we've engineered it. I'm not kind of saying, science is this way. This is just our idea. We had these 6 spare bits, so make this a 0. The function is how we then look up which particular operation I'm doing in the R space. Okay? So why isn't that a single 12-bit field? Well, we're going to see that we don't like to move our spaces around. Once I'm kind of locked in the leftmost 6 bits as opcode, it would be nice if that were the same for everybody. That's going to make my wiring much easier. The left 6 bits are always opcode, I just go from there. So rather than have to kind of have it, well, the 6 bits here mean this thing, but the next guy, it's over here. No, the opcode I start with, and if it's a 0, then I know that these 6 bits are live and are active, and not the lower end part of some immediate or something like that. Okay? So, RS, RT, RD, they're named as such because of the following. Source register is the S part, T is the target register, D is the destination register. So now you're saying, but Dan, it was so nice when you convinced me that when you have Z, I'm writing on the board now, equals X plus Y. I'm writing Z equals X plus Y on the board for those of you on the webcast who can hear it. And the leftmost guy got the data. He's the guy that got changed. And then you had add T0, T1, and T2, and guess what? The leftmost guy was the guy that got changed. But the way we've decided to wire it is it goes STD, where the D is the guy getting the stuff. So it's the last one, so it's a little out of order, and it always annoys me when I have to kind of apologize for the engineering of it, and I'm sure there are some reasons for it, but that's what that is. The D is the guy getting it, so this is RD, even though it's out of order from the STD. Okay, so it's a little annoying that way. Here's some more details about this. Anything I haven't already said? Oh, there's this cool guy called Molten Div. The way you multiply and divide is actually cool. And what's interesting about multiply and divide is you take two 32-bit numbers, when you multiply them, how big can the output be? 64 bits, right? Because if one guy was just one with a lot of zeros, you'd just be sliding the guy over, and that's 64 space. So it's 64 bits. So you actually want to have a 64-bit result. So I could not just say add T0, T1, T2, because this guy, the T0 is the guy needing to be 64 bits wide, but we know it's not. It's only 32 bits wide because it's a register. So mult and divide are also cool because divide, when you do a division of two things, you kind of get, what do you kind of get? You get a quotient and you get a remainder. So you also have like a 64-bit thing that you want to have. So it turns out that both of these guys, when you call a mult or div, they end up filling a high and a low register. Their output is not one of the normal T0s, S0s. They automatically write somewhere else. And then, like two special guys, and then you can bring the results from those guys with move from high and move from low. The only guys that ever stuff into high and low are mult and div, and the way you get the data from that is move from high, move from low, and those go into one destination, which is like move from high to one guy, move from low to one guy. It has one argument, really. Move from high to one register. That's how you copy your stuff into the registers, and then you can use that high or low. So this is just, we won't really focus on mult and div, but you can read up about them if you want. And shamped, as I said before, is the shift amount, and we can talk more about that, but that's just the shift amount from 0 to 31. So let's do it. Let's actually play with it. Here we go. Add 8, 9, and 10. 8's getting the guy, so I said 8 is the guy getting it. That's the destination. So this is the destination, RD. Then there's the source, which is typically the first guy, and S and T hopefully are the right name. So T is RS, and the other guy is RT. So DST is how it kind of reads across if you're looking at the MIPS guy. So I have 8, 9, 10 Shift amount is 0 because it's obviously not a shift. Shift amount should always be 0 for a non-shift value. That makes sense. It doesn't make sense to have a shift value and an add. No. Shift amount is always 0 unless you're shifting. And if you are shifting, then you care about those bits. But otherwise, it should be 0 just to make things easier. You actually ignore them in the hardware, so you could actually make them non-zero, but to do something clever, but you don't. You always set them to 0 to make it easier. The opcode we know is 0 because it's an R type. I said that before. And the function is 32, and you can look that up in the table in the green sheet or in the book. Therefore, this is how it lays out. We know opcode 0. 32 is the function number. Therefore, I am whatever 32 is in the number from 0 to 63 of R-type instructions. And I said before, it's like 8, 9, and 10, which is 8. Remember, the 8 is over here because it's STD. STD. So the guy getting it is the last guy over here. See, so 8 is the guy getting it now. That makes sense. It was 8, 9, 10 before as you read it left to right. See, 8, 9, 10. But it reads in the bit fields as 9, 10, 8. Each one of those maps to binary. So that's where, again, it's been useful. Not only you're going to see over and over, it's been useful to have that mapping of 2 to the xy to be a real number and vice versa. But it's also really useful to be able to say, I have a number, what's the bit field representation of it? So 9, bam, you've got 01, 001. You really want that. That's very, very useful. We're not going to have you do a lot of that, but it will ask you to do some of that. So you need to have that cold. And you can obviously write it on your sheet, but it's useful to have it in your head. Here's 10, which is 1010. That's kind of an easy way to remember 10. 8 is 1,000. 0, 0. 32 is this guy over here, and 0 is there. So therefore, there's my actual bits. You end up having an add. Z equals x plus y. I go into your code, and let's say x and y and z are stored into 8, 9, and 10. I go into your memory when your program is loaded, and I will literally find that bit string exactly. That's pretty cool. I'm telling you how to disassemble code now. You look at binary. You've never been able to parse that. You've never been able to load in an executable into Emacs. You still can't easily. But if you could, in an easy way to look at the bits, if you could somehow load into the mode where it actually showed you the bits per word, you would find exactly this line where it was the mapping of z equals x plus y. You'd see exactly that line. And over, I'm going to show you these things. As I start to reveal more of this thing, you realize, wait, you mean I can start reading binary executables now? Oh, yeah. Why don't I start reading the guy that does password coding? Have some fun. See if you can decompress that guy. That's kind of cool. So disassemble is the phrase for that. Try to disassemble your password encrypting guy. So here's this guy with the fields lined up. But when we actually go to hex, we break it into nibbles, right? So there's a nibble there, 0. There's a nibble of 2. You keep going. It ends up being 012A 4020. Or in decimal, this is 19,546,144, which is useful to nobody, but it's kind of cool that of all the possible numbers, of all the numbers from 0 to 2 to the 32, which is how much again? 4 billion-ish. That's and each one of them means something. If they were all interpreted as instructions, that would be, in theory, 4 billion different instructions you could have. That's the 19 millionth instruction out of 4 billion instructions. So I guess that's kind of cool. If you had them all line up, that'd be the guy standing at the 19 millionth spot. Questions? I've done a couple of slides without stopping for questions. I want to stop now. This isn't that bad. This isn't usually, it's more kind of engineering, explaining more engineering. So this isn't like teaching recursion, which is a whole brain busting kind of a thing. And this is how I broke them up into the nibbles. So that was easy. So this is the halfway point roughly. Yes, indeed. Appendix A has all this stuff that you want to know about. And there's some directives that you'll see about. Anything else I need to say from the TA point of view that I'm forgetting to say? We're good. Love it. All right. Anything else from the student point of view that I'm forgetting to say? Aside from maybe go to see Connected this weekend, which would be kind of cool. All right. So now we've done R. R is not too bad. I is a little bit more complicated. Because the only thing with R is the shift guy, which is a 0, then the op function, but everything else is pretty straightforward. I is a little harder, because you've got different guys in the I's. All right, so the 5-bit field does immediates, but that is not enough. We certainly want to do pluses and minuses. You want to have MIPS have one format for simplicity, but you couldn't. If you kind of went back to here, you'd have like a 5-bit immediate or a 6-bit immediate. That's ridiculous. That's too small. So what we do is, let's keep as much the same as possible. That's really the idea. So opcode, RS, and RT. That was the same as before, right? This was, now I'm saying, color chalk? I don't color chalk. So this x is now, this is guy plus 50 or something. So z equals x plus 50, okay? S and t an immediate. So 50 is the immediate. That was the obvious one, okay? Now, who's the guy getting it? Well, z is getting it. It was d. But look, there's only s and t here. So it's kind of annoying. In this world, this is the R style. For I-type, the guy getting it is RT. RT stands for target. What that means is with immediates, the target gets it. You're going to ask me, why couldn't you make it this destination for both of them? You're going to see why that is in data path time in about 9 weeks. So it takes a while to get to that, and you'll appreciate, oh, now I remember that whole question you have that, like, why is it just D? I remember the T is, I'll remember, like, I remember when I got that. That was really annoying. And you'll realize that doesn't matter. It actually doesn't matter how we do it. Like, you kind of pay the price some point. You'll see why this is different. So RT is the guy getting it here, and S is the source, so our one source is X, so S is still S. Yay, at least one guy's the same. All right. So I have here, T is the Z getting it, getting the value. This guy, T, is the guy getting it. S is the first argument. Immediate's the second argument. Okay? And what's our opcode? What are the values of the opcode? What can they be? Anything not 0. You guys are fast. The front, this row, these 3 rows are doing very well. Anything but 0, exactly. From now on, I don't look here. I want more people to talk. So from now on, you guys are verboten. Is that a word, verboten? You're not allowed to raise hand now from that 3 rows and back. More than 3 rows is there. So opcode's in the same place. We like that. That's going to help our hardware. We love that part. S and T, subtle difference with the fact that T is getting it versus D. That's going to come up in the data path, but we're going to see that actually doesn't matter. So we're getting the opcode. This answers the question of why I don't use a 12-bit number versus a 6, because now I have 63 I's and J's. I'll tell you how many I's and J's there are in a moment. Yes, question? Correct. I love that. That was much better than 6 or 5. Yes. That's a great question. What if it's bigger than that? Well, let's save that one because it's going to come up. We'll explain that whole thing. So, like on this slide. So 16 bits means that we always treat this as a signed number. So I can now do anything plus or minus 2 to the 15th, roughly. Okay? And that is large enough to handle the vast number of constants you ever have. You know, people don't usually put huge constants, but it's okay to do that and see. We'll see how to handle that. And it's also useful to handle most of the offsets. Remember, the offsets are usually when I'm explicitly saying int of A of 5, that's when the offset would be a 20, when you're manually putting a 20 there. Or when you have structs and you want to offset into the fields in the struct, like int x, int y, and z, that offset might be 0, 4, and 8 to get to the fields of my struct. So that's reasonable. And we'll deal with this next lecture, and the TA will cover that, how to handle that part. So let's do an example one. Add I. We know there's an I format because usually there's an I at the suffix of the instruction name. So add I. But you remember also load word and store word are also I's. So don't. It's not only the guys who are necessary but not sufficient for being an I format. 21, 22 minus 50. So let's look it up. Well, first we go to the green sheet. Add I is an 8. And that's our opcode. We know it can't be 0, so that's good. RS and RT are 22 and 21. We know that this is 21 is the guy getting it, and the guy getting it is RT, but it's STD when you read across. Remember that? STD. And here it's ST. So they stay in that same order, STD, in that same order. So you're mapping there. The guy getting it is 22, that's S, and this is 21 is the T. So how that reads, by the way, immediate's minus 50, so that's minus 50. And so this is how we write it. 8, 22, 21, minus 50. And now you say, how do you do minus 50? Well, that was just the lecture on number encoding. You look how to do that. And that's a lot of ones at the front with a 50 over here. This then gets clustered. This then gets clustered into the nibbles, and you have 22D5, FF, CE, and hex, or 584 million, blah, 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 as the ranked order of the instructions. Today is not so exciting. It's more kind of revealing how the stuff works. But this is going to be definitely useful for you and your project, because your project's going to need to know how the bits work and when you're doing it in a MIPS interpreter. Any questions? Yes?
What about labels?
Labels will come up. Labels are going to end up being an address. All these things are just address. So labels are going to be an address, and those are going to live. Well, those will be referenced here. If it's a load word, I have to figure out what the label is, what that distance is, and figure out that whether it's a negative number, is it above me, in which case it's a negative number, or below me, it's a positive number, and do that kind of thing. Based on, that's the offset. That's not based on the base pointer. Based on the base pointer, where am I going, essentially, with that number? Peer instruction. I'm ready for peer instruction. Unless there's questions. This really went much faster than I thought it was going to. Many questions you get. Yeah, I'll entertain questions from any row now. Yes, third row. Yes, excellent. The opcode determines the format. That's exactly right. How do I even know where the invisible field markers are? Am I the I, which I get a big 16 on the right, or am I the R, which all these 5s and 6s? The opcode determines that. Excellent. That's the best question. What's your name? Chris has asked the best question all day, which was, how do you even start? If I hand you some bits, how do you even start? It brings up the meta question of, there's a great book by Nicholas Negroponte, and I forget the title of the book, but it was done in like 87 or 90. Have you ever read the Nicholas Negroponte? He's the MIT Media Lab director. And he wrote a book that said, why do you ever hard code the format into anything? Why do I have a DVD format? There's no reason you have a DVD format. What you have is just bits on a DVD. Why is there the format for DVD? And oh wait, my player won't handle the new format. Ridiculous, he argued. He said, you should have somebody that can say from the basics level, start at the left, and the first couple bits are going to be some index into this. And if it's like some bits that are 0 through, let's say start here, right? Format, the first 6 bits, 0 means it's a DVD. The remaining bits you're going to get a DVD format. And then you have 64 different things you could have. Oh, no, that's too bad. What if you have 65? So what? Once you get to 63, then say, guess what? If it's 63, the next 10 bits are going to be how you do it, like our opcoded function. So you can have an infinite number of things, right? Now I fill up that one. No. When those maxed out, I use some more bits over here. You could have an infinite number of formats for anything you want. So he argues, why hard code anything into anything? Bits are just bits. Have some really smart interpreter that says, opcode, then it's a DVD. Opcode 1, it's a CDR. Opcode 2, it's a DVD from Japan. Whatever you happen to be, use those bits, because they have different region encodings, you guys know, right? So those different regions could be a different format. Japanese could have different, like, we might only have ASCII, so we might only have 8 bits for the subtitling. But if you're Japanese, you have more characters than 26, or than 127, or than 256 can handle. So you might have more bits for the actual Unicode for that. So my point is, why not? I believe it. I believe that you should not ever have a locked-in format. Well, you say, building hardware. Build an interpreter. Build something that's softer than hardware. Well, here we're building a really fast computer where we can't afford the time for that interpreter stuff. But the idea is, in general, and I think it's a really good point, you should never have any format at all. The whole book was about this idea. Bits should be bits, and then you download a file from the internet. I don't know what it is. Why? Because there's a lookup table. What are the first couple bits? Well, then it's a JPEG. Then it's a GIF. And you have these like headers that say that, but you should be able to have infinite number of file formats. And you kind of do. You have this headers, but you have to put them as file names. .jpeg is how you know it. Why can't the bits themselves tell you they're JPEG? Because the first 5 are this, and the second 7 are this, and the next say this, it's a JPEG. The remaining part of the JPEG. It's so smart. So anyway, that's a cool point. But great point. You start here by looking at the opcode. You got me off on a tangent, but I love that tangent. Ready to go. Yeah, question? I don't know. Nicholas Negroponte, 1990. Somebody find it on the web and tell me before TAs, go find Nicholas Negroponte. That's why I pay the big bucks. Yes? Oh, a big security hole. Tell me. Let's talk about it. Go.
Because people can manipulate the first bit and then they can change it to like an executable file or
So?
whatever they want.
Okay, well, so let's talk about it. So if I know if that table of what things are is published, then you could say take a JPEG and then change it and make it executable. And I guess that's true. But then you would look at it and you'd say, you're about to download an executable from the internet. Do you want to run it? And you'd see it because of the format. It would be just like clicking on like right now you click on a link and you don't know where you're going. I don't know what that link is telling me to, whether the link is it's a URI. That could be anything at the end of that thing. It could be a JPEG, it could be executable, it could be anything. Same reason. All I'm saying is, rather than have the file format say .exe and therefore your system knows executable, just have it be anything. You don't have any extensions. You just know the bits are bits. I mean, sure, there's a human readable part to it, which is I know on my directory it's a .jpeg, I know what it is, but the point is you don't necessarily have to have that. The icon could just look into the file and have a picture of JPEG. Yes?
Well, now you can still have embed executable stuff in JPEGs, and then you also have the issue of the hidden file name extensions in Windows.
Right. I want to make sure I have enough time. That's true. You still have hidden file extensions in Windows, which is true, and you could still embed executables in programs. They've been trying to sneak those things into QuickTime and some other things as well. Yeah, that's right. Last comment before we go off on peer instruction. Go. Oh, yeah, good. Good. Yes, PC is where I am. The instruction does not live in PC is not one of the 32. PC is a separate register. It's separate 32 bits reserved only for what you're doing right today. It's a separate it's like the 33rd register. But you can't index it by 33. It's just a separate guy, PC. And you can never directly change it until I tell you otherwise. You will be able to learn how you can change it later. But for now, you can't change it. The program is stored in memory. The program gets loaded into memory. No, it's in memory. It's in memory, that's it. We're going to see that it's loaded into a cache to make it faster, but essentially it's still memory. It's never loaded into a register, unless you want to load a register and start messing with it, but to having a rewritable program. But you don't load to run this ad of RSRTRD. You don't load that into a register and run it. It just lives in memory and you run it. It just works. Question.
Are there also different caches for?
They are different caches for instruction and data. We'll see that. I don't want to reveal too much, but yes, we'll see that. Yes.
Is the assembler written in zeros and ones then? Because if it was written by another language, then that language has to be written by assembler. Like, you know.
Is a bootstrapping problem? You mean how to that? I wouldn't worry about how it's written. It's just like you don't have to worry how the scheme interpreter is written. It could be written in scheme or in C or ones and zeros. It just works. It's an assembler. It's executable. It works. It helps GCC do this job. All right, let's try it. Peer instruction. Which instruction? I haven't been really good by asking a question that's hard enough that you kind of have different answers. Early on, I had some tricky questions, which were fun, but easy ones recently, unfortunately. Hopefully, this will be hard, so some of you missed this, so there's something to be learned. Otherwise, it's not much of a point. Which instruction has the same representation as 35? I look at the literal number 35. I map that back to binary, and then I map that back to what of the guys are here. And Chris's question is so relevant here. How do I even know where the fields are? And hopefully the answer you remember. I won't say it again, because that's part of the key thing. I'm glad you mentioned it, because I would have had to mention it right now, which would have kind of given it away. Oh, yay, the numbers are all on the board. Yay. Maybe the answer shouldn't be yay. Maybe it should be, oh, no, I didn't teach so well. That's not so good. By the way, just as a random thing, raise your hand. Who's going to see Connected, maybe? Raise your hand softly. Oh, not enough hands. You guys should go see it. The movie Connected. Go see it. That would be great. I might be there on Sunday, if I can come back. Wow, this is incredible. Are you joking, guys? Or are you really vote real? I mean, vote real, because I've got numbers that I've never seen before. This is incredible. I mean, really think about it and try to work me some stuff here. Wow. Are you kidding me? This doesn't make any sense. Go fast, so we can talk. Once we hit 175, we'll let you guys talk. Okay, talk amongst yourselves, but if you haven't voted, please do vote on this first one, if you're still waiting to vote. But talk amongst yourselves as you're doing it. All right, vote again. Come on back, vote again. Give me some love. That's more like it. That's more like it. All right. All right. Okay, somebody not in the first three rows. What do you think, guys? E, Y, E. Okay, let's start. Chris said, look at the opcode first. The opcode is all zeros and a 35 at the end, right? So opcode says 0. What do I know? R-type, right? R-type means I break it up into a lot of the things. So it's either going to be A, D, or E. A, B, or E automatically. And when it's an R-type, what do I look next? The rightmost 6 bits, which is arranged from what to what? 0 to 63. Therefore, I know I don't spill over to the Champ field or something weird like that. And it turns out that if I just look at the func, 35, it says here func is 35 is sub U. So I know I'm either B or E. And then am I S zeros or all zeros? All zeros, because the rest of the zeros are in the middle of that. What was weird about this was, you all did well, it is E, so I'll click on this guy here. But what was weird about this one was here, like for a while, it was all 25%. I had never seen that before. Like you all were giving me equal love on all A through E. It was like, let's share our pie with all 5 kids equally. And that was very nice of you. If you guys ever have kids, you want to share the pie all the time. So, in summary, I've shown you, this is pretty cool. I've lifted the hood. You now know how 1s and 0s in executables start to behave. It's pretty cool for disassembling executables back into C to figure out how they do stuff. We'll do more on Friday with the TA leading the charge. Thanks, folks. Have a great Thursday and Friday.